Hi all, let's see the next topic of Unit 1, Input Output and Interrupts. Let's see the contents. We're going to see about what is an input output organization. Later we move on to input output instructions where we come across interrupts. So coming to the input output configuration can be best understood by means of a terminal with a keyboard and a printer. Consider there is a computer with a keyboard and a printer, an input device and an output device. So if you look at this diagram, this particular terminal contains a keyboard and a printer, where the keyboard, the input device, has a transmitter interface connected to it, and the output device has a receiver interface connected to it. It acts as an interface between the computer system and the input output device. These two acts as an interface between the computer system and the peripheral devices. And each device, the transmitter interface, has a register connected to it. It's called as an input register, and the output device has a register called output register. So whenever the computer wants to take an input from the user through the keyboard, it goes through the transmitter interface into the input register. From the input register, the information is transferred to the computer through the accumulator register. Similarly, whenever the information has to be given as an output to the user through an output device, the information present in the computer is first transferred into the accumulator register AC. From there, it is moved on to the output register. Through a receiver interface, the information is transferred to the output device such as a printer. So coming to the input and output registers, these two registers are 8-bit registers which are capable of storing 8 bits of information. So whenever a key is pressed in the keyboard, the particular key, which is an numeric key, is converted into a 8-bit format, and through a transmitter interface, the 8 bits are stored in the input register. And if you see here, there are two flag bits FGI and FGO, used for input register and output registers respectively. So this FGI flag will be set to 1 if there is a content available in the input register that has to be loaded into the accumulator register. Similarly, if there is no content available in the output register, this FGO flag will be 1. So if the user press a key in the keyboard, the 8-bit information is transferred into the input register, then the FGI flag will be set to 1. So so the computer keeps checking the flag bit of the input register. Whenever it sees that this particular flag bit is set to 1, it means there is a information or data present in the input register. That particular information will be transferred by the computer into the accumulator register. Okay. Similarly, at the receiver side, at the sending side, whenever a computer wants to send the information to the user through an output device, whenever it has information present in the accumulator that has to be given as an output to the user, that it first checks the flag bit of the output register FGO. And if the FGO flag is set to 1, it means output register is free. So now the 8-bit information from the accumulator is transferred into the output register. And it again sets the flag bit to 0 because now the output register has a content. So from the output register through the receiver interface, it is displayed to the user such as printer through the printer. So once the input register contents are transferred to the accumulator, this FGA flag, which is previously set to 1, becomes 0. So that the user can, the keyboard or a transmitter interface can take the next character from the user and transfer it to the input register. So this is a terminal with a keyboard and a printer. So these two registers, input and output, communicate with a communication interface serially and with the AC in a parallel. So the transmitter interface receives the serial information from the keyboard and it transmits it to the input register. And the receiver interface receives the information from the output register and sends to the printer serially. So the input register is an 8-bit register which holds an alphanumeric input information. And there is a flag bit for the input register called FGI bit, which is a control flip-flop which can be set to either 1 or 0. So it is set to 1 when the new information is available in the input register. And it is clear to 0 when the information is accepted by the computer or when it is transferred to the accumulator register. So if you see the process of information transfer, initially the flag bit of input flag is set to 0. When a key is pressed in the keyboard, an alphanumeric code is shifted in the input register and FGI is set to 1. So the computer keeps checking the flag bit of the input register. Whenever it is set to 1, the information will be transferred from the input register to the accumulator, and once the transfer is done, FGI will be cleared to 0. Once FGI is cleared to 0, the new information can be shifted into the input register by striking the key in the keyboard. Next, coming to the output register. So the output register works similar to the input register, but the direction of the information flow is in a reverse manner. So if you see the process of information transfer, whenever initially the output flag FGO will be set to 1 whenever it is free. So when the computer keeps checking the flag bit of output register, if it finds that it is set to 1, the information from the accumulator is transferred into the output register and the flag bit is again set to 0. It is cleared to 0. The output device prints the corresponding character which is stored in the output register, and once the operation is completed, it again sets the flag bit of FGO to 1 again. So that if the computer wants to send the next 8 bits of information as an output, it can again send it to the output register. So this is how an output register works. So next, coming to the input output instructions. So the input output instructions are based on how the input output configuration works. So the instructions that provides a means of communication between the computer system and input output peripherals or input output devices, those type of instructions are said to be called as input output instructions. So they enable the data transfer from and to the input output devices such as your keyboard, your printer, monitor, etc. So with the help of input output instructions, the computer receives the data input from the user as well as it can also send an output to the user. So these instructions, they act as a communication interface between the CPU and the peripheral devices of a computer system. So when you compare it with the register reference instructions, in terms of instruction format, the opcode is same for both the register reference and input output, but only thing is with respect to the mode bit. This 12 to 14 bits is going to be 111, but the I bit is going to change. In case of register reference, the I bit is going to be 0. In case of input output instructions, the I bit is going to be 1. So the total opcode for input output instructions are 1111. But in case of register reference, it is 0111. And here, similar to register reference, the 0 to 11 bits, you doesn't require any memory reference. So this 12 bits are used to represent the type of output operation that has to be performed. So the input output instructions, they have an operation code of 1111 and are recognized by the control when the decoder output is D7 and I is 1. And the execution of these instructions also starts as a clock cycle T3 similar to register reference instructions. So each control function, it needs a Boolean relation. So the Boolean relation is D7 I T3. In case of register reference, the Boolean relation is D7 I dash T3. And this is represented by a symbol P. So if you look at the set of input output instructions, these are the list of input output instructions. So among this list, the last two instructions are considered as are instructions which are based on the concept of interrupts. So now let us see what is you mean by interrupts and then we move on to this particular table. So interrupt is nothing but the difference of information flow between the computer and input output device. There is a difference in information flow. If you look at the computer or the CPU, it is very fast in terms of transferring the information. But in case of input output devices, they are very slow. So there is a gap between the time taken for the information flow between the CPU and the input output devices. So rather than CPU wasting its time waiting for the input output devices to transfer each character at a time, it will transfer the information, 8 bits of information, into the output register or register, and it will wait. Rather than waiting, what it will do is it will continue doing the execution of some other program. So alternative procedure is to let the external device inform the computer whenever it is ready for the data transfer. So this type of transfer uses the interrupt facility, so that the CPU will not waste its time waiting for the external device, and the external device will doesn't require any CPU intervention to perform its task. So that here, in case of handling that interrupts, we are having a flag bit which is set. When a flag is set to 1, then the computer will be interrupted from proceeding with the current program, and it is informed of the fact that the flag has been set. So whenever this external device want the intervention of the computer to take the input from the input register or to give the output to the output register, then they will set the flag bit. Until then, the computer will do its own task. Whenever the flag bit is set, the computer will be, or the computer or the CPU will be informed that the flag has been set. So what the CPU will do at that time, whenever the flag is set, it will deviate from what it is doing, whatever task it is doing or whatever program that is being currently executed, in order to take care of the input output transfer. So after completing the input output transfer, the computer will return to the current program and continue with what it is doing before the interrupt occurs. So this is how the interrupts will be handled by the CPU or the computer. So we implement that in case of a flip flop called interrupt enable flip flop. So that is a flag bit which can be cleared to either set to 0 or 1. If it is set to 1, it means that this the particular external device want to interrupt the computer. So so uh, so the interrupt enable flip flop, whenever the computer wants to be interrupted by the external device, it will be it will do that with the help of a flip flop called interrupt enable flip flop. So if the interrupt enable is set, it means that the computer can be interrupted at any point of time. Okay, no matter whatever task it is doing, the computer or the CPU. So if the interrupt enable is set to 0, which means that the computer or the CPU does not want to be interrupted by any external device until the task is done, until it is set to 1 again. So that is done by means of a interrupt enable flip flop. So the interrupt enable flip flop can be set and cleared according to the two instructions as follows. I off means that it is set clear to 0, which means the input or output flags cannot interrupt the computer. If I on instruction means the interrupt is set to 1, it means the computer can be interrupted at any point of time. Now let us see the list of input output instructions. The first instruction is an input character in instruction that is used to take the information, 8 bits of information from the input register and place it into the accumulator. So as we know that the input register is an 8-bit register, but an accumulator is a 16-bit register. So the 8-bit the 8-bit contents of the input register is transferred into the 0s to 7 bits of the accumulator register. And previously when the input register has a contents, the FGI is 1. Now it has been transferred to accumulator, so the FGI contents will be cleared to 0. Flag will be cleared to 0. Next instruction is an out instruction. that is used to output the characters. So the contents of the accumulator 0 to 7 bits will be transferred to the output register, and the flag bit of the output register, after transferring the contents to the output register, the flag bit will be now be set to 0 because previously it is set to 1. Next is a SKI instruction, skip on input flag. This is used to check the status of the input flag. Based on the status, if the FGI flag is set to 1, then we are going to skip the execution of the skip the next instruction according to the program order. That is done by PC implies PC plus 1. As we know, PC actually contains the program counter. It contains the, it points to the address of the next instruction that needs to be executed by the CPU. Next instruction is SKO, skip on output flag. So this is used to check the FGO, the flag bit of the output register FGO. If it is set to 1, then you are going to increment the value of PC by 1, which means that you are going to skip the execution of the next instruction according to the program order. Next are with respect to the interrupts I-on and I-off. If the in case of I-on, interrupt enable is set to 1, which means that the computer or the CPU is ready to take the interrupts from the external devices. In case of I-off, if it is clear to 0, which means that interrupt enable off, the CPU is not ready to receive any interrupts from external devices. So this is the set of input output instructions which are a part of computer instructions. So if you see this table gives you the overall set of computer instructions which are classified into 3 types: memory reference instructions, register reference instructions, and input output instructions. We have already seen the memory reference and register reference as well as input output instructions.